sliding, right? For that
Mhm.
that kind of thing. So, is it like a is it like when two parties enter into communication, there is kind of some locks which synchronize like the access to like the communication channel between them, or like it
Mhm.
is always open? Like that was another question that I had from that.
I'm not sure if I understand. So can you just maybe summarize it one more time? So if you say there are three of them, how the algorithm is expanded to, like, extended to three players? Is that your question, or is it something else? I didn't.
Yes, Professor. Like in while generalizing this two-party to multi-party context, like how would the picture transform into like, uh, uh, for instance, like uh, one party could be populating all the answers. Let's say the first one announces his wealth. The other one, who's like damn wealthy, says that he has the wealth, like more wealth than whatever he has stated. So all S's, and the third party might like override the information, and when finally he sees it, like the information that he perceives might be different, might not be accurate. So
Yeah, so I mean, there are protocols. I mean, generally, I mean, in this lecture, we're going to talk a little bit about more formally about secure multi-party
okay,
computation. Specifically, we're going to talk about what's called a Yao-Garvel circuit. Again, there we're going to give you a two-party example, but there are ways to extend this to multiple parties. One simple thing that you can think of is like the easiest solution for this would be the first two kind of like, share the results, then the second one and the third one, and then so on. So basically, always we kind of have like a partial sum idea that two of them partially compute something and then goes to the next one and goes to the next one and so on. So that's one way of doing it. There is another notion called secret sharing, which essentially the secret is shared among, the assumption is that the secret is either naturally or intentionally shared between different users. Then there are methods for addition mainly and multiplication, how we can do addition and multiplication when we have secret share. So what happens there is that everybody's kind of partially shares some of their information to the rest. Everybody kind of like add their partial sums or compute the partial multiplication. Then there will be some sort of like one of them would becomes an aggregator that gets everything. Of course, again, the trust here is that nobody trusts each other. So the algorithm is designed such that somebody just get all these partial sums without actually knowing exactly what is getting. So there are algorithms for extending this to multiple parties as well, easily. But yeah, we're gonna mainly focus on two, but we're gonna discuss how we can actually extend it to multiple as well.
thanks, Professor.
All right, so there's one thing in chat. In the case of simple comparison, this problem should not be there. Alice would simply answer no to every part. So I'm not sure which part she was referring to, but yeah. Somebody else raise hand. Kiarash?
Yeah, hi, Professor. I have a
Right.
question. In the target model extraction attacks, can we call all of the extracted models shadow models, or the shadow models only used in the membership inference attack?
So the terminology is different. So some people call it like knockoff models. Some people call it shadow models. Some people call it, attack models. There's really not a universal terminology, unfortunately. Shadow model, I find it the most useful and most intuitive one. So generally, shadow model is any model that we're trying to replicate. All right, so that's what we are trying to do. The goal of the attack could be membership inference and could be model extraction. But what we are trying to do is basically replicating the original model, and we call that shadow model, right? But again, it's not something that you will see this consistently in all the papers. So some people call it different things. So expect to see that, unfortunately.
Okay.
Well, at least in this class, when we are saying shadow model, what we mean is any model that the attacker tries to replicate. And the goal is really doesn't matter. It could be membership inference, or it could be model extraction, or it could be even model inversion.
Got it. Thank you.
Is threat model different than attack model? Not really. Usually it's like, people use threat model. So attack model really, it's not, I mean, threat model is what we are, because attack model really is more of like what assumptions we are making about the attacker. But the threat model is generally assuming what is the general assumptions about the whole system. What we are trying to protect, what are our weaknesses as a defender, what is the goal of the attacker, and what is the capability of the attacker. Remember in the first lecture, I talked about these two things, right? So what is we trying to protect? What are the weaknesses? What is available for the attacker to steal, right? And then on the attacker side, what the attacker tried to achieve, what are the capabilities of the attacker, and so on and so forth. So threat model is usually more generalized concept that's consider all of this. Attack model is more of like, what the attacker tries to achieve. But again, I've seen people who are interchangeably use these two terms together, but tries to use threat model because it's more popular and more standard, right? Okay, so let's continue. So last time we talked about various things, but the last thing we talked about was the notion of privacy preserving, right? If I go back. We talked about the notion of privacy preserving, and we said that essentially privacy preserving is that we want to do some arbitrary computation, in most cases just a polynomial computation, where the input data is coming from multiple parties, and multiple parties do not trust each other, and there is no third-party centralized trust as well. So what we need to do is coming up with some decentralized algorithm in order to evaluate that function. And we said that there are multiple different approach for it. We're gonna mainly focus on these two. I don't think we will have time to discuss the others. So what I'm gonna do is probably at the end I'm gonna I'm gonna shoot a short video over the weekend or something and send you just like a very basic idea of what the others do. For these hardware-based, we are going to extensively talk about in the next few weeks. But secret sharing, differential privacy, and non-cryptographic, I'm going to give you just very basic overview of what they are. All right. So let's go to. All right. So we said that we want to create, so we're now talking about homomorphic encryption, and we said that homomorphic encryption is just something that we want to encrypt two values, and then hopefully if we can add or multiply those encrypted values and then decrypt them, we get as if that we added those plain text values, right? And the last thing that we kind of discussed was this crypto systems which use eigenvectors and eigenvalues. And we said essentially that, eigenvectors and eigenvalues, it has this nice property that if we create a matrix based off the eigenvectors, based off the eigenvalues, and a shared secret, which is the eigenvector of both of these, matrices, if we add these matrices, the eigenvector still remains the S. And the eigenvalues still becomes the summation or the multiplications of the eigenvectors. All right. So this would be our potentially homomorphic encryption system. The problem, unfortunately, though, is that as we discussed, this is not a secure method. The reason that it's not secure is that given C, it's easier to find M and S. It's kind of like, searching through space, but very quickly the attacker can find M and S. And finding either of these is basically considered breaking the encryption algorithm, all right? So this is not secure. So what should we do? We need to come up with, so people actually come up with this very neat idea, and that's what's called an approximate eigenvectors, all right? And the way it works is based off this very interesting problem called learning with error problem. So this is a problem that has been defined in 2005. And what the learning with error problem is basically saying that if you have a system of equation in let's say in Z, natural numbers, and if this in basically a subset of, this is Z, basically, let's say everything mod 17. So we are basically dealing with numbers between -16 to 16, right? So what we have is that if you have a system of equation like this, of course, if this is just a normal system of equation, we can easily solve this and find all the, variables such as S1, S2, S3, and so on and so forth, depending on how many variables that we have. But the learning with error problem or LWE problem is basically saying that if we create the system equation with some errors, so if we basically this equation that we have here is not exactly correct, but is correct with if we add some errors, the same term error for all of them, then what happens is that this problem becomes very hard to solve. There are mathematical proof for that why this is a hard problem. But what it's basically saying is that if we go back to analogy of our eigenvectors and eigenvalues, if we have this, normal equations that we had before, and if we change this to this equation here, which basically saying that, CS is equal to MS plus some small error, then this becomes what is called the LWE problem. And there are mathematical solutions that shows that this is actually very hard, an NP-hard problem to solve. All right. So probably those of you who've taken algorithm course are familiar with what NP-hard is, but those of you who do not know like what the terminology of NP-hard is. What we're saying is basically there is no known solution that in polynomial time we can find a solution for this, right? So in polynomial time, we cannot find a solution for this problem, all right? In other words, we cannot find M or S in this. If we cannot find M, S, for example, in this case, even if we have C and S, right? So that's what the basis of a secure homomorphic encryption is based off. There are the actual, more formal description for it. So for example, there's a parameter N, a modulus Q, and some error from some probability distribution X, which is X is over ZQ. So when we are saying ZQ means that a subset of, integer domain of Z, all right? So for example, previous example, Q was 17 in the specific case, right? So if you have some distribution, we draw, errors from that. And then what if we just basically uniformly choose a random vector from this Z and Q. So basically, we choose from ZQ n different elements, and we call it vector A, right? So we get A that is basically drawn from ZQ, and then we use it a uniform distribution to choose from this. And then if we choose E as a single number again from ZQ, so if we get E from ZQ, and then if we form this equation here, which basically AS means the sigma of AI SIs, right? So this terminology here is basically just element-wise multiplication and summation. And if we add this term to E and then do all of these mod Q, and then say that this is T, finding a solution not knowing S, we cannot find A's basically, all right? So that's what the learning with error problem is. How do we fix this? How do we create this? Well, let me actually jump over this. So basically the way that we create our encryption system would be something like this then, where the idea is our P or S in the previous example would be our secret key. The R would be our noise. B would be our message. Let's say in this case, B is either 0 or 1. And then in that case, our encryption would be C, all right? So what we're gonna do is that we're gonna send C and A, and that would be the encryption that we are sending. And given C and A, it is proven that without knowing what R is, the attacker cannot find what the original message, which is B in this case. This is our message, all right? So this would be our encryption method. The decryption method would be basically C mod P. So here, the user actually has access to the P, which is the secret. So the first thing that the user, the decryption algorithm will do is that it computes C mod P, and then it's going to do mod 2 in order to get rid of these 2R components as well. And what it gets is actually B. So remember, C was A P plus 2R plus B. So what it does is that this C mod P will get rid of this. This mod 2 can get rid of this. And what we get as the encryption would be RB. All right. So this would be just basics of how our encryption algorithm work. And if we test it with the addition and multiplication, we will see. I'm not gonna, because of the time, I'm not gonna go through it, but that could be one practice for you guys. So it would be A1P 2R1 times B1, and then we are adding this with A2P 2R2 plus B2. If you add them together, you will see that we get something like A prime P plus 2 R prime plus B1 B2. And we can, this is basically would be our C3. And if we decrypt this, we'll see that these terms go out, and what we get is B plus B1 plus B2. All right, so we'll have the addition with for the addition. The same thing if you do, you will see if you just multiply this term by term, again, we're gonna get some values. And if we get rid of the mod P and mod 2, again, we're gonna get B1 times B2, all right? Because if you multiply this, there will be a term that we have here that would be B1, B2. The main thing that's gonna happen is that our node is gonna grow, so we're gonna talk about that. But let's actually go back and see why our encryption mechanism is hard. All right, so far, is there any questions? So maybe I went through it a little bit fast, but let's see if there are questions here. So somebody asking what A is here. So A is just a random vector that we are sampling from CQ. So it's like this, basically. Our A's are this coefficients here. All right, so we are randomly sampling it from some domain, let's call it ZQ. All right. Any questions? Choice?
Yeah, I'm not sure if this makes a lot of sense, but I was wondering how when we do the mod 2, is there any chance that would actually affect the message as well?
No, the message would be just a single bit, which is B is always 0 or 1.
Oh, okay.
Yeah, it's just a single bit.
Okay, thanks.
Yeah. Can you mention briefly once more what Z is? Z is just, natural numbers, sine natural numbers, right? So -3, -2, Z. That's it. Any other questions? Okay, just to one more time, briefly going through it. What we are doing here is using LWE, learning with error problem, to create our crypto system. Basically, what we are saying is that we have some secret, call it P, and we have some message, call it B, all right? So what we are doing is basically getting this A in random from some subset of Z, so let's call it ZQ. And then what we're going to create is a system of equations. And then we're going to add an error term called R, which is just a number in ZQ. We're going to do it 2R just because to make our decryption a little bit easier. And now we're going to also add kind of like hide our message under this. So what we're going to send to the open world is basically C and A, all right? So we're going to send C and A to the open world. And there are mathematical proofs that, given A and C, the attacker, if not know what P is, they cannot find B, all right? So there is mathematical proof for that, which quickly we're going to a little bit talk about this at the intuition level. And this way, we're going to show that if we add, C's together, like if we add C1 and C2, or we multiply C1 and C2, if you actually decompose this and open this and do the actual multiplication, you will see that this is actually, after the decryption, you will see that, it's as if that we are adding B1 and B2, or as if we are multiplying B1 and B2, all right? And for the decryption, basically what we do is that now we are assuming that we have the secret key, right? So this is like a symmetric key encryption systems where for encryption we use P, for decryption we also use P. What we do first is that given C, we do C mod P, and then we do the results of this mod 2, and that will give us P, all right? So again, if you look at the equation, you will see that C mod P will get rid of this, mod 2 will get rid of this, and what you will be end up with would be B. All right, so that would be our encryption and decryption mechanism. So hopefully now it's much more clear. So let's go back and see why this is actually a hard problem. Any questions so far? All right, so the hardness of this LWE problem, which is the basis of homomorphic encryption. So first of all, there are multiple different, types of homomorphic encryption. We are just talking about one basic one, right? So the hardness of this problem is actually coming from what's called lattices. Probably most of you already know what lattices is, but you can think about the lattices as this domain that has some bases, and based off those bases, we get different points. So for example, what I'm showing here is the 2D lattice that we all of us are kind of familiar with. Like this, let's call this here 0, 0. This would be probably 0, 1, 0, 2, and so on and so forth. This would be 1, 0, and so on and so forth. And for example, let's say that our basis would be these two vectors here. All right. So what lattices will give us is that any linear combination of these two bases, if it's a 2D, we have some sort of like base 1 and base 2. Any combination of let's call it XB plus YB2 will give us a point in the lattices, all right? So that's how we actually build our 2D systems, right? So for example, this would be 0B1, 1B2 will give us to this point, 0, 2 will give us to this point, and so on, right? So points in our lattice word is basically what we care about, all right? And this point here, which is kind of like, let's say this is, for example, let's actually move it to here. So this would be, for example, 2.5 B1 plus 1 B2. So to get to this point, we need to do that. And since this is not, a valid coefficient, because our coefficient should come from some sort of ZQ, this is not a valid point in our lattice, all right? So basically all we care about in our lattice word is points, and points are linear, combination of our bases. So knowing the bases, we can create our points in our lattice. How is noise introduced? So let me talk about this, and I'll come back about the noise and talk about noise as well, all right? So this is like of course, very simple lattice, but lattice could be NDs, so it could be n-dimensional, and of course, it would be very difficult to show it in a 2D word in a piece of papers, but we can create lattices here as well. All right. So why LW is hard is basically because this problem in lattice word, which is called a closest vector problem. There's also some other models for and some similar algorithms that this problem reduced to, but the one that we are basically going to talk about is closest vector problem. And the closest vector problem is basically saying that if we don't know what our bases are, so for now assume that we don't know what B1 and B2 is, it would be hard that given any arbitrary points, such as this point, this green point here, to find the closest vector to the closest lattice point. So basically what we're looking here, for example, is this vector here. So if we don't know the basis and we are given any random points, let's say a point here, finding the closest vector to this point from a legitimate and correct lattice point is a hard problem. Of course, in 2D, it's not intuitive because you can clearly say that, okay, it seems that this is the point that we are looking at. This is the vector that we are looking at. But if n is large enough, so if n is bigger than some threshold, n means the dimensionality of our lattice, it is shown that there is no known algorithm for finding this in polynomial time. All right, so if we don't know the basis, this would be a hard problem. If we know the basis, then there are no known algorithm for finding it. All right, so this is what makes the LWE problem hard. Then there is there is, as I said, there is reduction from this algorithm going all the way to LWE algorithm, but this is not an algorithm course, so we're not going to talk about it. But just know intuitively that if we have a lattice system like this that has some bases, and we don't know that basis, so that basis becomes the secret. If there are some random points in this lattice, knowing that there is finding that closest vector from a legitimate lattice point to that point is a hard problem, and cannot be found on average in polynomial. All right, is that clear? Anybody has a question here? So it's a little bit of an abstract concept, but I think hopefully it will be clear if you think a little bit about it enough. Any questions here? Okay, so this would be the basis of why LWE problem is hard. And based off this assumption, then we can create our crypto system. All right. So basically, as I said, our crypto system would be something like this, where if you want to put it actually into context of some sort of lattice, you can think about that our correct lattice points are these zeros, P's, P2, P3, P, and so on and so forth. And the way our encryption works is that by adding this 2R plus B, we are slightly moving the points from an original lattice point. All right. So basically, this would be our C. All right. So again, I'm showing it in 1D, but of course, it's not a 1D. It's n-dimensional. But to make things easier for you guys to understand, I make it in 1D. All right. So the idea is that if the adversary does not know exactly what are these valid points are, finding this this C and finding this B, basically, that's what the adversary really wants, is hard. Of course, as soon as you know what this P is, then you can do mod 2 and then get rid of these 2R, and what is remain becomes your P. All right, so that's the basis of kind of like very intuitively how this encryption mechanism works. Any questions so far? So back to Hari's question of how the noise is introduced. So all we need to do is that the noise should be coming from this domain. So basically the noise should be some sort of smaller than this size. And since we are doing 2R, basically noise has to be smaller than this half size between these two. All right, so the noise should be smaller than P2 in this specific case. In most cases, this is actually some sort of like Q plus 1 and so on. So the noise should be smaller than that. All right, that's how we create our noise. Evan?
Yes, is that NP hard for any dimension?
If the dimension is larger than some known values, yes.
Thank you.
Yeah. So again, if it's like a 2-dimension or 3-dimension, you can find it. There are no algorithms for it. But if n is bigger than usually, I think these states 128, then it's hard to find. There's no known algorithm for finding it. Any other questions? Okay. And now if you think about the decryption, basically the decryption is that the decryption system, the receiver, let's call it Bob in this case. So Alice is sending something to Bob. So Bob knows what P is. So it can quickly find exactly where this point is in this domain. We'll get rid of this. Let's say here is 0. So we'll get rid of this part here. So what it remains is this part here, which is 2r plus b. Again, we're going to get rid of the 2r by just doing mod 2. And what remains would be b, right? So that's the way that we're going to recover this message that is kind of buried inside our lattice system. Any question here? Cool. And as I said, this is just a simplified example. In reality, what happens is that P is actually a vector and C is a matrix, all right? So basically our A's and P's are vectors and our C's are matrix. So we are dealing with n-dimensional, all right? So it's not like simple as one-dimensional. And the reason for that is that search space that we are reducing to some sort of closest vector, it has to be larger than some threshold, otherwise it's not a hard problem. And I already talked about this, probably you can just go through it. But the key thing that you need to understand is, unfortunately, the biggest challenge with homomorphic encryption is that as we do addition or multiplication, our noise grows, all right? So for example, if you look at here, our noise for addition, our noise grows linearly. So we will have a term like 2r plus 2r2. So our new noise, which we call it R3, is basically R1 plus R2. So anytime we do addition, we are growing the noise linearly by the inputs, all right? So if you think about the bucket of noise that we have, let's say initially the bucket is small. As we do addition, we add a little bit more. Then the next addition, basically this noise will be added with a new noise. So the bucket will get fuller and fuller. And then it gets full until at some point it's just too big, all right? And we're gonna say what happens if the noise is too big. But just remember that, as we do homomorphic encryption, specifically addition, the noise grows linearly as factor of R1 plus R2. And even worse is the scenario for multiplication, because in multiplication, what happens is that we're gonna get a term such as 2R1 times 2R2. In other words, we're going to get 4R1, R2. So actually, we'll get a multiplicative term of noise. So noise is basically not even added linearly, but added in a multiplicative way. It's a more exponentially grows, right? So if there were no noise added, can the attacker crack the code and get B? No, right? So because knowing the A, the attacker can easily find this lattice points, right? So get the B as well, because this would be just a normal system of equation, right? So in that case, the attacker can easily just solve that system of equations. The whole point is the LWE problem, which adding some noise. Otherwise, that becomes a normal, or remember eigenvalue and eigenvector problem, which essentially is a system of equation. There are methods known for it, such as Gaussian noise reduction and so on, that the attacker can easily use and recover the message, right? So that's the issue. So without noise, this is not a hard problem. The attacker can easily crack. Is that clear, Arunchalam? No. All right, so the noise grows, and for addition, the noise grows linearly. And for multiplication, unfortunately, it grows with an exponential factor, all right? And if the noise grows too much, I mean, again, if you think about it in an intuitive manner, going back to our 1D formula, when we are doing this, mod 2, mod P, if these points become closer to this point, what happens is then we are basically, the errors kind of wrap around, and instead of getting B, we are getting B plus 1. So basically, instead of getting 0, we get either 1, or instead of getting 1, we get 0, right? Because the noise goes into the neighbor points, and then we are basically, when we are removing the noise, we will move to this point, and then basically our B's would be something random. Could be 0, could be 1. So the noise cannot grow from half of this point, otherwise it will just goes into the near neighbor, and our decryption would be incorrect, right? So unfortunately, what we have is some sort of noise budgets in our system, all right? And what this means is that if whatever this budget is, so let's say we have a budget B, And then let's say each addition grows the noise by x1, and each multiplication do that by x2. So basically we either, for example, if you assume that we can only do additions, we can only do this amount of additions in our homomorphic encryption mechanism. Or even worse, we can do this amount of, multiplication in our system, right? And as I said, this is actually grows in a exponential factor. So this is not even this, right? So what happens is basically we kind of like cannot do infinitely. We cannot add. Because at some points our noise, we are kind of like reaching to our maximum noise, and the system will no longer work. So there's no guarantee that we can recover our B correctly. So what is the solution for that? There are two main solutions. One is what's called a leveled or somewhat homomorphic encryption systems. And the other one is called fully homomorphic encryption systems. The difference between these two is the first one is kind of assuming that, okay, we have some budget. So what we can do is basically assuming that we know what our function that we want to evaluate on is, we basically can just, find how many addition and multiplication this has, in offline phase completely, compute what would be the biggest noise at the end of this circuit. So think about this as some sort of a circuit. And we can basically say, okay, each addition and multiplication, how the noise grows. And then at the end, the output level, we can know exactly how big the noise will be. So if the budget that we create would be bigger than this point here, then we are good to go, right? So we don't have to be worried about anything, right? Of course, this has two downsides. First of all, we need to know which function we want to apply to this network. So that's the first issue that we have. The second issue is that we need to, if this is like a very deep function, let's say we want to do some sort of like a multiplication for deep neural networks, then this budget has to be really, really big. All right, so this budget has to be so big that you can actually do, let's say, 9 or 10s or it's more than that layers of computation in a deep neural network, right? So in that case, we need to come up with a really large noise budget. And how does noise budget is actually defined? The noise budget is basically, again, intuitively, is the distance between these points in our lattice, all right? So how do we make this distance bigger? It basically, you can think about this distance as the size of the inputs, the size of the intermediate values. So let's say we want to multiply x1 and x2. If this one is 128 bits and this one is 128 bits, this size, there is a specific noise associated with this. If we increase this and make it 256, then it means that there is more room for the noise to grow. So which basically means that we are essentially moving these points apart from each other, right? So this one moves into this direction, this one moves into this direction. In other words, if we increase the size of the inputs, we are basically increasing our noise budgets, all right? So the bigger the inputs are, of course, the noise budgets would be bigger. So that's intuitively what we want is to use bigger size inputs. But what's the penalty of using bigger size inputs? The penalty of using bigger size inputs is that now instead of multiplying 128 bits to 128 bits, we are multiplying 256 bits to 256 bits, which means that if there is a power or latency associated with each single bit, we are make it 4 times bigger, right? So every multiplication takes 4 times more, every addition takes 2 times more, etc., right? So this means that more power, more latency, more energy, and so on and so forth. So it's kind of we are reaching to this trade-off points where at some point we want to have a bigger budget because we want to evaluate deeper networks. But on the other hand, we are dealing with the overheads. So as the budget goes up, the overhead also goes up. So we need to find some sort of a balance between these two. So if you want to evaluate deeper networks, we need to be willing to pay that overhead penalty as well. Is there any question here? Okay, so that's what's called a level homomorphic or somewhat homomorphic. The thing that happens in 2009, if you remember, it said there was a breakthrough. Well, this concept of bootstrapping, which essentially say that, you know, there is a trick that when the noise actually gets to the maximum, what we can do is kind of decrypt this and re-encrypt it again. So what it does is basically, if we decrypt this and re-encrypt it again, it's as if that we kind of resetting the nodes. The way that this decryption and encryption works is something complicated that of course is beyond this course that I'm not going to talk about. But there is this very nice algorithm that's what it does basically. You can think about it very intuitively as we are switching the key. So let's say we are using S1 for encryption up to this point. What we do is that we using this another function, which we call it switching, you know, key switching function. But basically what it does is that it gets this C1 and creates this C2. So this would be our new encrypted, our new ciphertext. And at this point, this C2, the difference between C2 and C1 is that the noise in C2 is reset. So it started from 0. And now we can continue our evaluation. The price that we are paying is this key, running this key switching, you know, algorithm, which actually, unfortunately, very, very expensive in terms of multiplication, addition, and so on. But there is an option that we can do this. And how this can be helpful? This basically means that we can do infinite number of, you know, homomorphic multiplication and addition as we want. We just do a certain amount. Once we reach to the point that our noise is at the maximum, we do the key switching, our noise kind of get reset, and then we continue. And then this would be an iterative process. So at some point that again, we reach to the maximum, we do the key switching again and again and again until we reach to the end of the inputs. The good thing about this is that we don't need to then create this large budget. So basically our noise budgets would be the frequency of which we need to do the key switching algorithm. All right, any questions here? So this process here where we kind of decrypt and re-encrypt the data, the input data, the ciphertext is called bootstrapping. Again, I didn't go through the details, but basically very intuitively the bootstrapping is, again, homomorphically do the encryption and decryption. So you can think about the encryption and decryption as a function itself. So what we can do is that we can do the decryption under the homomorphic encryption itself. We can do encryption under the homomorphic encryption itself. So that's where we can do the key switching. So all we need to do is basically decrypt using another key and encrypt using another key. And this way we kind of like, you know, reset our system with nice. All right, so hopefully it's clear enough. Any questions? All right, so I already talked about this. The main challenge in homomorphic encryption these days is the performance. And the reason for that is that regardless of whether we are using FHE, that is the fully homomorphic, or SHE, which is the somewhat homomorphic or level homomorphic, the problem that we are facing is that our normal computation, which usually is like, let's say 8 bits times 8 bits, becomes large things such as 128 bits times 128 bits if we use something like an FHE. If we do use something like SHE, which is somewhat, if we want to evaluate some deep neural nets, then we go through like something like 1,200, something like that, right? And then this is just pure multiplication. Just think about something like machine learning where you need to do millions and billions of this addition and multiplication. So the overhead is actually skyrocketing. Unfortunately, these days, the normal overhead that we are seeing is 3 to 5 order of magnitude overhead. So that's the numbers that we are dealing with. So if a normal inference, for example, takes 1 millisecond for something like a deep neural net, in homomorphic encryption, we are talking about seconds and tens of seconds. So usually it takes like around 10 seconds for just one single inference, right? So for example, now put this in the context of training, where you need to do millions and millions of iterations of this, this will take days and even weeks to do a simple training of a network, right? So that's what we're dealing with these days, that homomorphic encryption can give us this incredible opportunity that essentially the server do not see anything and do not learn anything about our inputs. But on the other hand, we're paying this significant penalty of performance, right? If we do FHE, we get some of these performance saved, but unfortunately, on the other hand, this key switching, this bootstrapping algorithm itself is very expensive. So that's also kind of offset the amount of data that we save here for the noise. So it's again, it's a it's a trade-off between if you want to use FHE or SHE. There are new algorithms that does FHE much more faster. So there are research going on in this field that, okay, how do we bootstrapping much more faster? Because if you can make the bootstrapping much more faster, then probably we can, improve the performance of the overall system. But again, this is like an ongoing research. But overall, what we are dealing with these days is 3 to 5, order of magnitude slowdown, which means that in many scenarios, unfortunately, homomorphic encryption is not feasible, right? Any questions here? Okay. The second problem in homomorphic encryption is coming from the fact that homomorphic encryption can only do polynomial activities, right? So we said that we only do addition and multiplication. We didn't talk about nonlinear operations, right? So for example, specifically in machine learning, we have things like, ReLUs or tangent hyperbolic and this kind of stuff. And unfortunately, homomorphic encryption cannot handle those because they cannot be shown as linear polynomial operations. So what we can do for them, there are two class of solutions. One is you can always approximate these to some polynomial. So for example, something like 1 over S2 could be a good estimation of what the ReLU is. So ReLU is kind of like, looks like this. 1 over S2 is kind of like, looks like this. Right, so it's kind of an estimation of what the ReLU does, but of course this can bring some noise to the system because we're, substituting ReLU with another function that is not exactly that. So there are research going on and whether we can, we need to retrain the system, what would happen, how the error propagates, what we can do in order to reduce that error, and so on and so forth. All right. So the research these days are basically among two different flavors. One is mainly at the algorithm level, at which we're thinking about, okay, what sort of machine learning maybe innovations that we can make in order to, for example, deal with like the absence of nonlinearities in homomorphic encryption, but at the same time being able to use homomorphic encryption. What we can do, for example, to make homomorphic encryption much more faster, there are some approximation mechanisms that can be used. Another line of research is around hardware acceleration and designing specialized hardware. The idea here is that if we can, so the assumption is that we want to run homomorphic encryption in probably a general purpose CPU. What we can do is creating this accelerator that is specially designed for, let's say, doing homomorphic multiplication and addition, because this is basically, as I said, homomorphic is basically just adding polynomials to polynomials or multiplying polynomials to polynomials. So maybe one thing we could do is that designing a hardware that can do this much more faster than regular CPUs. And in that case, we can hopefully, bridge the gap between this huge performance overhead that exists between normal computation versus homomorphic computation. So this is another line of research that these days are being used a lot. Probably, I think somebody going to present a paper in this domain as well in the upcoming weeks. Anybody has any questions? All right, so the second thing is, I guess we don't have much time, so I'm just going to wrap up and then let you guys start presenting. So the second thing is what's called multi-party computations. We already talked about millionaire's problem and intuitively give you some idea that how we can, for example, evaluate a function, which in this case was if A is bigger than B, and do that without actually revealing what A is and what B is. We extensively talk about other scenarios where, of course, by doing this, we're going to reveal some information and so on. But the idea is that both of them are willing to reveal that information. But what they are not okay with is actually knowing exactly what A and what B is, right? So millionaire's problem was like one of the very old problem in this domain, but there's a more systematic way of doing this. Another example that we can do is sum of the numbers without revealing individual numbers. So let's say we have A1, A2, all the way to AM. And what we want to do is getting the sum of AIs from 1 to M, right? And of course, one possible solution for this would be that, you know, a server, an aggregator get the values and then do the summation. But again, in the absence of such a trust, what we can do is use some sort of, you know, multi-party computation algorithms. In this case, for example, the solution is, so let's, for example, let's say that there are n players, that only one of them is malicious. So starting from A1 all the way to AN, and one of these are the malicious user. So what we can do in this case is that the simple algorithm for this in homomorphic encryption is that let's assume that everybody is sitting some sort of a circle. So what A1 gonna do is that A1 gonna, like, instead of sending A1 to the next person, which is A2, A1 gonna do A1 plus some R, which R could be just a random value from 0 to some number. All right. So what the first person gonna do is they're gonna send A1 plus R to the second person. The second person, what the second person would see is A1 plus R. So of course has no idea which part is R and which part is A. So what this next person gonna do is that basically gonna add their number to the sum that it gets. So basically to the third person is gonna get A1 plus A2 plus R. All right. Again, the third person has no idea which part is the actual summation and which part is the noise. This process continues until this last person, AN, gonna get A1, A2, all the way to IN minus 1 plus R. This person, now the key is that this person gonna send this value here plus IN to this person here, the first person. And the first person, since already knows what R is, what the first person gonna do is that gonna get this value subtracted by R, and that would be the sum that everybody is looking at. So it's gonna announce the sum to everybody. And if you think about this methodology, at each point, nobody knows exactly what is the exact value of the previous person is. The only thing that they get is some sort of running sum of the overall sum plus some R. And the last person, when by sending back the sum to the first person, the only thing that the first person can do is just removing the noise and announce it to everybody else, right? Of course, the idea here is that we are assuming that there's only one malicious player here, and everybody is just getting the data from previous person and sending the data to the next person. Of course, if these two people collude with each other, what they can do is that this person sends data to this person. This person, instead of actually, sorry, this person and this person collude with each other. So this person sends the data to this person. This person, instead of actually sending data to this, sending the data back to this person. And what they can do is that just by subtracting these two values, value here and value here, they can figure out what this value was, right? So including two people and do some secret communication, of course, break the system. But here, what we're assuming is that there's only a single malicious user and everybody else is just following the protocol. There's a specific terminology for this, which we usually say honest but curious, which means that everybody honestly follow the protocol. But of course, everybody is also curious to know what the value of the other people are, right? There's kind of a combination of everybody following the protocol, but not really cheating in the protocol bubble. They're trying to cheat that in other levels. And another important assumption that here we have is that only there's one malicious. If there are multiple malicious users, then probably this method won't work because two of them can collude with each other, do the connection to each other, and break the systems. All right. So any questions here? Okay. So the assumptions really matters, right? So the assumption is really important. And in MPC, we need to exactly know what are the possible number of malicious users, what is allowed and what is not allowed, and do this and design our algorithm based on that, right? A more systematic solution for this is what is called Yao-Garwell secret. In fact, there are multiple different solutions for this, including the GMW protocol. What I'm going to briefly talk about is the GC algorithm or Garwell circuit algorithm. All right. So in the example that I'm going to give you, GC is between two parties, but actually it can be easily extended to multiple parties as well. The key idea in main observation in GC is that basically any problem, any given problem, including like finding the max or finding the sum or anything else, what the GC does is that first it's translate this problem in some sort of gates. All right. So basically think about this is that we want to basically find the logics, we create the binary logics for this. So we create some form of gates from any given algorithm and given problem. So anything that can be shown by gates can be solved by GC, right, as a multi-party computation. And what we do is that basically each gate will be shown as some sort of truth table where for truth table, we have inputs and outputs, we have zeros and ones here, and we have zeros and ones here. And what we're going to show you later on is how we do this truth table and gate evaluation using GC, right? So that's the main observation. So the first thing that we do in GC is defining the problem in a circuit domain, all right? And the second thing is that now we need to kind of evaluate these gates. So what we do is that if you have a complicated system of multiple different gates that goes and connected to each other and goes forward, it could be many layers. What we need to do is evaluate each gate one by one. Once I show you that how we can evaluate each gate, then you basically can move forward and evaluate all of these gates one by one. And once we do that, we can start from the inputs and go all the way to the outputs. And this way, we're going to get our results that we want, right? So specifically what we're going to focus on would be an AND gate. And our assumption is that there are two people here, Ginny and Ivan, that each of them has one of the inputs. And of course, what they want to do is evaluate this gate. So the truth table will look like something like this, obviously. If it's 0, 0 would be 0, 0, 1 would be 0, 1, 0 would be 0, and 1, 1 would be 1. Classic AND truth table. And let's say this is actually the inputs from Ginny, and this is the inputs from Ivan. All right. So we don't have much time to talk about it. What I'm going to do is that I'm going to record a very short video discussing GC and then probably other algorithms in privacy preserving. And that would be it for our discussion on privacy preserving. Next week, we're going to move on to another topic. All right. So if there's any other questions, let me know. Otherwise, we can move forward with our paper presentations. Questions? FHE. So somebody asked what is the difference FHE and SHE? So FHE stands for fully homomorphic, and SHE stands for somewhat homomorphic. Difference is this, that somewhat homomorphic, as I said, homomorphic encryption generally is something that, you know, the noise grows as you do it, addition and multiplication, all right? And since you're assuming specific size for the inputs, it means that your noise budgets is smaller than some known threshold, all right? So your noise budgets would be smaller than some threshold. If you, for example, do 10 addition, your noise grows and becomes bigger than some values that you can no longer recover your original message, all right? Think about it as terms of SNR in signal and systems, right? So if the signal to noise ratio becomes smaller than some values, you no longer can recover your own signal, right? So this is somewhat homomorphic encryption, that essentially you're assuming some budgets and you're saying that the maximum amount of operation that it can do is this amount based off this calculation that you have. The fully homomorphic encryption fixed this issue by introducing the concept of bootstrapping. So basically what the bootstrapping does is that when the noise becomes that big, you need to do this operation called bootstrapping, which essentially changes your ciphertext from one domain to another domain. And in this new domain, basically what happens is the noise is reset. So now you have a fresh ciphertext, then you can do another set of homomorphic encryption operation. And you can do this infinite times. In other words, you can do any sort of, you know, a function that you want without being worried that your noise would be, your SNR would be dropped so low that you can no longer recover the system. The price that you're paying is the price of bootstrapping, which is something very complicated. But if you want to do very complicated functions, that's the only solution that you have. All right, hopefully that's solved the question. So let's go with the first presentation. Actually, let me open it from here. Let's see if I can find the chat.
Hi, my name is Simon Sherber.
And my name.
Oh, okay. So I can actually I have to pause sharing from here. Sorry. Give me a sec. All right, can everybody see this screen? Yeah?
Yeah.
Yeah, okay, cool. All right. And you cannot hear it, right? You cannot hear it.
I think it's paused.
No, I know it's paused, but it's can you hear it or not?
I cannot.
Yeah, because I need to.
Would it be easier for me to just play it on my screen and then share it?
Yeah, that would be okay too. Yeah, I don't want to play it from my speaker because then you get lots of other noise. Or
I have it open on my screen if you can.
okay, yeah,
give me...
go ahead and start sharing.
Let me know if you guys can see.
Yeah, we can see it.
Okay.
Go ahead and start it.
I don't think the audio is going through. and the defenses on.
Yeah, we can hear.
You can hear that.
Thank you.
Server.
And my name is Edwin Calderon.
And we researched a paper titled ML Leaks, Model and Data Independent Membership Inference Attacks, and the Defenses on Machine Learning Models. So what specifically is a membership inference attack? It's a type of privacy attack where you're trying to learn about the data input. More specifically, you're trying to determine whether or not a data point was actually used to train a model or not. And this has some consequences, such as you can start to be able to infer some things about the machine learning models for the inputs. And this can lead to learning information about health statuses, social network information, mobility, and other types of things. So this membership inference attack was initially proposed by Shokri et al. And in this paper, he was able to show that these attacks are both possible and effective. However, one of the downfalls was that he had to have some pretty harsh assumptions in order for this type of attack to work, such as he needed multiple shadow models, he needed the same or similar structure known as target model. So you had to know a little bit about the machine learning model in advance. And then also you had to have data sets from the same type of distribution as the target model. So this is labeled training data. And the question that this paper was specifically looking at was, could we relax these assumptions and still be able to have an effective attack? So before we start to dive deep into how these types of attacks actually work, we kind of have to talk about the background structure of how these ML models are attacked. So commonly today, machine learning as a service is happening. And basically what this is internet companies such as like Google will start to create these machine learning models based on some hidden or private labeled training set. And they will basically allow this to the public as a paid to subscription kind of, and they'll have it in a black box where you interface with an API. You can send in images or different type of data, and they'll send back labels based on their machine learning model. However, it is obviously in a black box, so they try to hide it. And the only way, one of the setbacks is that you can, in theory, attack these by querying inputs and looking at outputs and trying to infer things about what's going on inside of this black box. So it is vulnerable to attacks, therefore, and can expose private information about how it's trained, steal the models about it, or specifically attack the model. So the defenses that most of these machine learning services have to try to prevent these kind of attacks are paper query. So if you were going to have an attack that needed to do a lot of querying, it could be really costly and not feasible. Along with, if there is high amounts of query rates or unusual type of querying that wouldn't look like it's actually trying to use the service properly, they have alert systems as well. So getting into the specifics of how membership inference attacks actually work on these MLAS systems. So like I said before, the desire of these attacks was to basically see, was a data point in the training set that was used to create the machine learning model. So there's kind of two main points of how this attack works. So the first is the shadow training. So basically what happens is the user generates some query shadow training sets, and he or she then tries to generate what's called the shadow model, which is supposed to mimic the machine learning model, or multiple shadow models as in the previously used. And you basically want to see that it is able to match the machine learning model as best as it can. One of the limitations is you have to know the training set and have the data. And the second part of this is that you need to create an attack model, which is based off of these shadow models. And basically what this attack model does is that if you feed it in data, it'll say whether or not this data it believed was actually used to train this machine learning model. So the goal of this paper was basically to look at, can the attacker have these successes of the attack with using less queries. So they were looking at using only specifically one shadow model rather than multiple as used in the past, have limited access to similar training data. So not the full entire data set that the machine learning model we use, have no knowledge of the target model structure. And by no knowledge, there's a little bit of leeway for that. In their terms, they use it as they know it's a neural network, but they don't know any of the hyperparameters specifically about the neural network and how it was tuned. And then also they have no knowledge on the algorithms that were used or the classifications that was used for the model when they were trying to make these shadow models. So what is the motivation for doing this? Like I said, it's more realistic, the less of these assumptions that you have to have. So for example, if you have less shadow models, it leads to less queries. So you're less likely to have the system is triggering alerts for having a lot of the queries, less expensive to attack. You have to use less queries. And then also, if you're an attacker, you don't have to have knowledge of the model completely. So this might be hidden and this is more feasible. And then also you need less of a need to have the exact data set that the machine learning model would have trained on. And so with this plan, they advise 3 different kinds of adversary attacks, and we're able to compare that against previous papers. So the 2 types of evaluation metrics that they were looking at were precision and recall for this membership inference attack. And specifically, precision quantifies the number of positive class predictions that actually belong to the positive class, whereas recall quantifies the number of correct positive predictions made out of all positive predictions that could have been made. So if you're an equations kind of person, precision is the true positives over the true positives plus the false negative, whereas recall is the true positives over the true positives plus the false negatives. So it basically looks at how accurately is it flagging to say whether or not a training was in the data set. And it basically just gives a precision answer to see how accurate it was. So every time it does this and then flags something, it's a binary answer. So it's either incorrect or correct if it wasn't in the training set. And then you're able to basically compare these data sets, recall and precision versus the previous papers with the relaxed assumptions and see how much of a decrease or how much of a change that these relaxed assumptions have on the precision and recall. And then also they started to look at assessing what kind of defenses could be used to stop these membership inference attacks and see how effective they are at reducing the precision and recall.
As seen here and previously mentioned, there are 3 adversaries with their own set of assumptions. I will reintroduce them as they become relevant. Overall, the assumptions are relaxed as we move from adversary 1 to adversary 3. The purpose of the paper is to establish a comprehensive piece highlighting emerging and developing threats of member inference specifically, and the solution can be reframed as an extension of what is currently being evaluated. In particular, the paper uses the findings of Shokai, as mentioned, as a baseline to highlight how the paper develops the understandings of existing attack and defense methods in the context of member inference. This is a major appeal of the paper since it established benchmarks within a continuum of possible scenarios that are realistic. The baseline implementation of Shokai uses 10 models to attain ground truth membership with a dataset that comes from the same distribution, and that the shadow model uses the same machine learning algorithm and has the same hyperparameters as the target model. It is important to note that this is a very ideal situation since it removes a lot of barriers for an adversary. The assumptions are relaxed in the sense that only one shadow model and one attack model is used. Some notable results are that this implementation works for balanced and unbalanced datasets, and that better results are seen for datasets with more classes. Another important observation is the observation that their attack has a very similar membership inference as the previous work, and also shows that a combining attack can free the attacker from knowing the target model entirely. In this scenario, for adversary 2, the assumption relaxed is that the adversary has a dataset that comes from the same distribution as the target model's dataset, as well as model design assumptions that were relaxed in the previous one. This is a data transferring attack meant to mimic the target model's behavior. Overall, the evaluation shows a 0.93 precision and 0.92 recall for some datasets, some on the value benchmark of 0.88 and above, but there are exceptions as seen in figure B where no grouping is clear. Another point to highlight is that datasets from different domains can effectively attack other models. So as our assumptions become more and more relaxed, we're seeing that their applicability widens, and from a security and privacy perspective are more concerning. For the third adversary, no training is done, and statistics are used by querying random points to the target model to get corresponding maximal posteriors. As the figures show, our random points maximal posteriors behave similarly to the distribution of the non-member points, which leads to the strong membership inference. And the figure on the left shows how these metrics perform without a single set threshold on data statistics to confirm maximal performance. There is room, I think, in future work to explicitly state how these methods performance may deal with datasets that don't have clear bounds for their features. Comparisons and adversaries. The figure here shows the performance of the 3 attacks and show that both adversary 1 and 2 are highly accurate with regards to precision and recall. The third adversary with the minimal assumptions is only slightly worse, especially for precision. The results show that membership inference attacks are very broadly applicable and of high concern if you're looking at it through a lens of security and perspective. Defense mechanisms. The paper explores the other spectrum of attacks by exploring how defenses can be implemented to mitigate the attack studied. Dropout is a good characteristic in defending a model due to the inherent overfitting nature of machine learning models, since if we query with the member that the model was trained on, then we will get a high posterior. Model stacking reduces the attack's performance on the location dataset by more than 20% for the precision and 30% for the recall for adversary 1, I believe, but exceptions do exist and there are trade-offs to evaluate, specifically when we are looking at the parameter for dropout, since we don't want to reduce the accuracy of the training model. Most of my questions and comments are informed for other readings in regards to the advancements. And the data paper here, models and assembling methods have its own practice and limitations, so there may be room to expand on more of the decisions made that make a model more robust in certain cases. Since the paper highlights that there is certain configurations that make a model more robust, it is not, I think, intuitive to want to configure models with different low accuracy thresholds over a model that is accurate throughout uniformly. Models that are based on neural networks, so the implementation for the defense here was specifically for models that are not based on neural networks. It would be interesting to see what would be applicable for the other one. And also specifically evaluation on MLA services was not done on the cloud or explicitly stated as in other sections of the work where it was explicitly called out for. And I think there is also more work to kind of explore how applicable the defense mechanisms would be for the attacks here specifically, because my understanding from reading other papers is that defense mechanisms work specifically well for one set of attacks. So it would be interesting to explore how other attacks would be able to mitigate security and privacy implementations here. And these are our works cited, and thank you.
All right, that's great. So kind of over time, but let's see if there are questions. So one thing that you guys can definitely do is follow up on the discussions of each paper in Campus Fire. So I guess the last slides could be a very good starting point for having some discussions. So hopefully I'll see some offline discussion on this matter as well as, you know, similar things, questions about the papers and so on. So use definitely Campus Fire for this kind of discussions, all right? All right, so next is Jinhan and Arunchallam. Tell me your first name as well when you're doing the present. So are you guys have a recorded video or are you doing it live?
We'll do it live. I'll share
Okay.
my screen right now.
Yeah, go ahead.
Can you guys see my screen?
Yeah.
Okay, perfect. Okay, so I'll start. Hello everyone, my name is Jinhan Wang, and today I'll present a paper named the DRMI, a data set reduction technology based on the mutual information for the black box attacks. So first, let's see what's the problem this paper wants to tackle. So consider the black box attack. So technically it's inevitable that attackers need to query the system inside the black box and get the prediction results or the classification probability vectors, or just those scores and use those information to train a substitute model. So the primary idea of this attack is quite simple, but there still remain some challenges for the adversary regarding the number of queries. It's generally believed in this area that large number of queries are costly and infeasible. So for example, as referred in this paper, for a complex data set, ImageNet, it requires hundreds or thousands of queries to train a substitute model. And it will also be at the risk of exposing the adversary. Another thing that exact training data is also not accessible. And sometimes the commercial used models are trained using a mixed publicly available and confidential data set mixedly, and such as the Amazon, Google, and Facebook. So this paper is aiming to solve the first challenge and leave the second challenge as a byproduct of their achievement. The main challenge is the limited number of queries when actually implementing the black box attack. The most important assumption in this paper is the existence of the redundancy within the dataset. So consider two cases shown in this page. The left one stands for the similar digit 0 in the MNIST dataset. And it can be guessed that the responses from those samples would be similar. And on the other side, those 4 digits on the right side have larger differences. They are skewed to a bigger degree, and responses can be more powerful if we can use those 4 queries to train our substitute model. And then the problem can be concluded as follows. And how can we select the high quality and also with low redundancy data for the efficient black box attack? So next, let's talk about the data reduction a little bit, regardless of the black box attack. So data reduction is a technique that can not only be applied to the black box attack. So generally, any task or project which requires a smaller data set can apply this kind of method. And its opposite is the data augmentation. So consider the figure down below. So given the raw samples on the leftmost, by applying the augmentation, we can generate more samples and better modeling distribution as a circle. And on the contrary, the reduction is a process to simplify the data set by minimizing the redundancy. And as shown in the figure in the reduction, by eliminating some samples which are closer to each other, the distribution is not affected to a bigger degree, it's still a circle. But we can speed up the training in this case because we're using less samples, so the number of batches could be reduced. So similar to the data augmentation, where new samples are augmented into various domains, the reduction can also use different similarity measurements to do the reduction work, such as the structure similarity based on the luminance and other aspects, and cosine similarity based on the angle and the simplest LP norm between 2 samples. And in another domain, we can classify some existing methods into 2 main categories, namely the model independent one and model dependent ones. So the model independent means the reduction is done in advance of the training. So the process doesn't require any knowledge of the model itself. So for example, the correlation matrix of the dataset. On the contrary, the model dependent methods are those who need the information from the model. So for example, the class probabilities and activated neuron trees omitted from the model. And then I'll hand over to Aaron, and he'll introduce the solution, contribution, and also the evaluation methodology used in this paper. Aaron?
So the solution the paper has brought is using mutual information from information theory. So this gives us the similarity between images. As you can see on the left, the formula for mutual information for images is given, and it's defined using in this paper as such. Here, R is the maximum pixel intensity value. Generally, it's 255, and PU of I is the ratio of pixels of a particular intensity I in the image to all the pixels in that image, and UV of ij is the ratio of the number of pixels with which has intensity I in image U and j in image V, and they both should be in the same coordinates and to the total number of pixels. And if you see at the bottom, we have 2 graphs. So they are converted to a graph theory problem. So let's imagine we have 6 types of zeros, which are shown in the left, and we need only 3 of them. So using mutual information, we need to select the 3 samples. So here the samples will be the vertices, and the mutual information would be the weights on the edges. Next slide. So here we'll define H. So H is the sum of the mutual information between the samples, and we need this to be as minimum as possible. So we shall select the set which gives the most minimum H value. And the H uses an I matrix. I is just the mutual information which is raised to some power alpha. We shall discuss about the hyperparameter alpha in the evaluation. So we convert this to a graph theory problem as I spoke, and the problem is it's a NP complete, so we cannot solve it using brute force. So they have developed an approximate solution to this particular problem. Yeah, so this is the approach they have used in this paper. So first we'll choose a particular data from the data set, and we'll input it into the selected set, which is S0. And then we'll use greedy choice initialization to select all the, and we'll build an initial set using using greedy choice. And then after the initial set is developed, we'll swap out the pairs so that the H value reduces using one-hot replacement optimization. And then this would go in a loop. We'll choose a different first sample into the data set and carry this out, and then select a set which has the least H value.
So quick question, Aaron, is the goal is like select a predefined set of points? Is it like, 3 is like in your example is 3 is the one, or you're just looking for a subset that has a minimum? My question is more of like, yeah, go.
It's looking for a subset, but the number of elements in the subset is already fixed.
Already fixed.
Yes.
Okay. So then the number. Okay. So they're looking to find the maximize among the fixed values.
Yeah. So if we have 1,000, then let's say we need only 100, then the first initial choice S0 would have 100, but it's not optimized. So they replace the pairs. They replace some samples to get more.
So they're trying to find the subset of 100 that has the least amount of redundancy, or the most amount of differences in terms.
Yes. So initially so first one of the data is chosen into the S0. So let's say S0 is a selected set, and using greedy choice, all the 100 samples will be chosen, but the 100 samples is not the final set. It will go through the one-hot replacement optimization, which I shall talk about soon, and it will remove some samples and add some samples, but the number in the set will remain the same as 100. So in the initialization step, they use two methods here. So one is the min-sum method. In the min-sum method, it chooses a sample which has the least mutual information to the already selected set S0. So if you see on the right, S0 has A, D, and F. So let's assume that A was chosen into the S0 initially, and then if you look in the row of A, D has the least information, mutual information with A. So D is introduced into S0, and then F is chosen because it has the most minimum sum of mutual information to A and D. So we get a set S0 as A, D, and F. In the min-max method, it's very similar to the min-sum method, but just that it chooses the least maximum mutual information to the selected set S0. Yeah. So after we build our initial set S0, we have to use iterative optimization here. So here, a particular data set, a particular training sample will be thrown out and a new sample will be introduced, but there's a condition on when it happens. So the condition is the H value should decrease. If that's the case, then they would be swapped. The pairs would be swapped. So here, for every sample, we'll have some of the mutual information values of a particular sample to all other samples in the selected set S0, and we'll choose the sample which, so if you see on the left, B has the highest mutual information in the set. So there are 3 elements in the set B, D, and F. So B seems to have 1.13. So that is the highest in the set. So B, it's possible to replace B with something else from outside the set. So when we look outside the set, we find that A has only 1.08. So A would go into the selected set and B would be thrown outside. So this keeps on happening until the H value converges and we're no longer able to swap out any more pairs. So this is a final selected set using iterative optimization. So in the evaluation step, they've implemented this on Python with PyTorch library. And using this, they have developed adversarial examples, and that is also evaluated using the targeted projected gradient descent method. In the evaluation, it attempts to answer 3 questions. How effective is DRMI in reducing data? And how effective it is to conduct black box attacks, and compared to other reduction strategies such as correlation matrix or trace, how does it compare and what can be interpreted from its results? In the experimental setup, they've used all image data sets, namely the MNIST, the CIFAR10, and the ImageNet. They also compare it with 2 other methods, the baseline method, which is randomly selecting a specific number of samples, and the manual reduction method, which is using humans to go through the images and select the most non-repetitive images from a particular data set. So the results of the evaluation will be shown by Jin Han.
So next, let's look at some results. So in this session, some tables may not be the same as what you actually see in the paper, because I think the paper doesn't manage those tables well. They are referenced anywhere in the results section. So I rearranged them a little bit for better clarity, and also some tedious results are omitted. So the first problem is how effective the data reduction method is in the training domain, regardless of the black box attack. For question 1, this method evaluates 3 domains. The first is evaluation on different data sets. So as shown in this figure, the author evaluated DRMI in this domain on 3 different data sets and 4 different models and their different number of queries, which is the size of the simplified data set, and compare with the baseline manual selected data size. So table 1 shows the performance on the minutes using the model Linai 5. It shows that DRMI outperforms manual and baseline regardless of the number of queries used. Also, the proposed 2 methods, min sum and min max, doesn't show a significant difference. And table 2 shows the evaluation on CIFAR10 using the ResonNet 18. Because the 2 methods of DRMI behave almost the same, the min sum, the min max. So the author omitted the experiments for the min max in the following experiments, and they only apply the min sum. And it can be seen that the DRMI still performs better than the baseline under different number of queries. And here the AD size stands for the number of samples the DRMI can view to extract samples from. And in table 3 is experiments on the ImageNet using the Inception v3 and the ResonNet 152, which are a more complex data set and task. The DRMI still outperforms the baseline to a great extent, even when the number of queries are far less than the baseline, like the 50K, 20K, and 10K. So those evaluations of DRMI on different data sets showed a great generalization capability over data sets with various sizes and complexity. Hello? Yeah. Can you guys hear me?
Yes.
Yes, okay. So the second domain of the question 1 is to evaluate different reduction in rate. So from the figure, we can see the DRMI outperforms the state-of-the-art product methods and the baseline greatly when the data size is restricted to be small, specifically larger than 60, but smaller than 600, 1%. And besides the curve, the author also evaluated this method when the attacker can only have access to limited in-domain data with a matched distribution, and out of domain data without a matched distribution. So in table 2, the provided different sizes of in-domain data, the DRMI can still achieve a great performance, even only 1% of data is accessible compared with the entire data set. As shown in the last column, for the minutes, we have 60K, but there only 600 is used. And table 5 shows that even provided out of domain data, the performance doesn't downgrade much compared to the in-domain experiments. So it also provides a remark that the DRMI allows the attacker to have a very small data set or without knowing the exact training data with a matched distribution. And the last domain is to evaluate the method on different models. So the author measured the test accuracy on the MNIST using 2 different models named the C3F2 and DN5. So C3F2 only stands for convolution 3 and the fully connected 2, which are mainly based on the convolution structure, and DN5 is structured based on the fully connected layer. And results shows that the DRMI can still achieve better performance than the baseline, no matter what the architecture is, and but further prove that it's generalization on different model architecture. The second question is how effective is this method for the black box attack? So in question 1, the author showed this method can be used to get a good simplified data set, and the trained substitute model can have good performance. So how good will the adversarial samples generate from this substitute model? So to measure the attack in a quantitative way, 2 metrics are used. So accuracy is just a traditional accuracy measurement to represent how good the substitute model is. And transferability is the success rate of the generated adversarial examples. I'll use the AEs in the following context. So the attack performance is compared with other 2 state-of-the-art methods called Prada and Practical under different number of queries for the targeted AEs on the MNIST. And it's obvious that the DRMI yields a much better performance for all of them to a great extent. And for the untargeted AEs, the DRMI is compared with the gradient estimation on MNIST and some other methods on the ImageNet, and the results still reveals advantage of the DRMI compared to those methods. And the final question left to us is how does this method work compared with other reduction methods? So table 8 compares the DRMI with the CMAL, which is a model independent method called correlation matrix active learning, which is done in front of the model training. It shows that the DRMI outperformed the CMAL for both the test accuracy and test loss under the same epoch. But actually the test accuracy and test loss, it basically says the same thing. And correspondingly, the table 2 compare with the DRMI with other model dependent methods, with the high-low class probability, the k-means and trace, which are those methods based on the input output or the state of the model after refeeding the data. And DRMI is still the best among them. So I'll hand over to Aaron. He will introduce some of the strengths and limitations of this paper.
Yeah, just very briefly, Aaron, please.
So the strength is that it uses mutual information. That is a novel way to reduce data, and that it uses an algorithm to solve an NP-hard problem. And coming to the limitations is that it doesn't seem to compare other known metrics such as SSIM for reducing the number of samples, and it's not applicable for dynamic systems such as speech. So maybe a proposed solution could be using an upper bound on mutual information estimation.
Why wouldn't be, I mean, we don't have much time, but I mean, I'll be curious, why wouldn't be mutual information wouldn't be, I mean, you can on the fly compute the mutual information even for speech, right? By dynamic system, you mean I mean, not knowing the mutual information beforehand? Is that what you're saying?
Yeah, I mean, this dynamic system actually the dynamic signal, since the mutual information in this paper used is based on the intensity. There are quantized intensity within the image, and the image has a coordinate system that is static. But actually for the image, this signal is dynamic. So we cannot calculate the mutual information purely based on the distribution of the intensity. And also it's implicitly true that the mutual information between 2 speech cannot be calculated solely on 2 different vectors.
Yeah, I mean, but I guess some notion of distance metrics is always what probably can be done, right? Like, for example, maybe cross correlation for a time series would be an option in this case, right? So like how
Yeah.
there are known methods for speech that to measure the similarity, like cosine or normal cross correlation. Anyway, we don't have much time, so let's move on.
Sure.
But yeah, okay.
We only have one slide left. So there are some future work direction that worth investigating. So first is a parallel topic to the data reduction called the data desolation. So data desolation is a process to extract information from data set, generate new one, and samples are not exactly what we saw in the real data set. So the paper I referenced has already applied this method to get a great performance in the data poisoning attack, but adverse attack hasn't been investigated yet. So that's one possible direction. Another one is the model-dependent DRMI, since the method proposed in this paper doesn't utilize any information from the model. So if the information from the model state and output can be used to further refine the quality of the data set, the performance may be improved further. That's it. Thank you.
Thanks a lot. So again, questions, discussions, please follow it up on Campus Fire.
I'll also open the thread about the data desolation for your references, and also you can comment if you want. Thank you.
Yeah, of course. Thank you. Yeah, that's great. Just one quick comment that I have for both presentations is that since we're going to share this probably on YouTube, it would be great if you use any figures that you use, either cited properly, or if you create it unknown, then that should be fine. But make absolutely sure that every figure that you're using is cited properly. All right?
Sure.
Okay. So I guess we won't have time for the fourth, but let's do the third, and then Shreyas and Vishnu, we're gonna move yours to next week. Sorry about that. So Shu and Gaoliang, go ahead.
Let me share my screen. Sure. Can you guys hear me?
Yes.
Okay, great. Share my
also pronounce your first name, so I don't make
it. Yeah. Okay, Shu do that. That's not the first slide.
Starting from last.
Okay.
Cool.
Hi guys. So my name is Shu Wang, and my teammate is Guoliang Chen. The paper we are going to review today is high accuracy and high fidelity extraction of neural networks. Machine learning as a service is popular today. For example, users can send a cat image to a service called ImageCode, and the ImageCode will use their model to do an image classification and tell the user that this image is a cat. The problem is if the users are malicious, they want to extract the model that ImageCode is using. The malicious user will learn the input and the output of this service and try to steal the inner model. This is an example of model extraction, and there are potential security and privacy concerns related to this attack. So when extracting a model, there are two factors that attackers want to improve: accuracy and fidelity. The figure illustrates the difference between accuracy and fidelity. The solid blue line is Oracle, which is the model that attackers want to steal. It may have some arrows in before the orange and the blue line here. There's 4 arrows. It does not classify the red export symbol and the blue symbol with 100% accuracy, but it's okay, because the green line represents higher fidelity compared to the orange line. It keeps the arrows the Oracle made. You can imagine that if the more closer the green line is to the blue line, the higher fidelity the green line represents. And the orange line represents higher accuracy compared to the Oracle, which classify all the points correctly. So it fixes these 4 arrows. So here are some prior work on model extraction attacks. For example, the existing attack made by Trimmer et al. And Millie et al. The former one used active learning to improve accuracy, while the later one used direct recovery to get functionally equivalent model. So the authors mainly work on improving these 2 existing attacks. So Here are the main contributions also present in this paper. The first, as we mentioned above, they classify the space of model extraction attacks by exploiting two objects, accuracy and fidelity. And then learning-based model extraction is used to achieve high accuracy. They also use two semi-supervised learning techniques, rotation loss and mix match, to improve the query efficiency of the attacks. Also, this model is scalable for larger models, such as with larger parameters, more parameters. And for high fidelity, also develops the first practical functionally equivalent model extraction on two-layer neural networks. Besides, they mix the proposed methods to obtain a hybrid method which improve both accuracy and fidelity extraction. And Guoliang will talk about details about this.
Yep, so our paper is considerably more simpler than their paper. So I'll go into the details about how they improve the model extraction in both accuracy and fidelity. So first, let's talk about the learning-based model extraction. This will increase the accuracy of the model extraction. So all the prior work use supervised learning to extract model, and then that will use the Oracle as the label data machine. Basically, it gets all the training data from the Oracle and then try to reconstruct the model the Oracle use. However, this method is inefficient, and then I'll show later that it's not very, it used a lot of queries to achieve the same accuracy as the following one. So the author used semi-supervised learning instead. Because in an attack, what mostly happen is you have a lot of unlabeled data that is available online that you can just download. So you use the Oracle as the very precise, accurate prediction machine to get some labeled data. You use that labeled data and a lot of unlabeled data to train your model. By using this semi-supervised learning, the model accuracy can be improved by a lot. So here's a simple graph to illustrate that. The malicious user queries the Oracle and then gets some labeled data, and then use both that and the unlabeled data to train their model. So here's are the results that the paper listed. The author trained two versions of the same model, with the only difference is the training algorithm. So on the SVHN dataset, one used fully supervised training and then other used mixed match, which is semi-supervised training. As we can see, with 250 queries, the fully supervised training only achieved around 80% accuracy. But with the mixed match, the semi-supervised training, we're able to achieve 95% accuracy and 96% fidelity. That actually surpassed the 4,000 queries using fully supervised learning. So author here shows that semi-supervised learning can improve the accuracy and the fidelity of a model by a lot, but that is scaled to a larger data set. So the author also did the same thing for the ImageNet, which is a much bigger data set and has 1,000 classification rather than like CFAR 10 or SVH only have 10. So the baseline accuracy, which is the fully supervised learning, the accuracy is 83.5%. However, with the semi-supervised accuracy got improved by 3% to 86.17%. So the author showed with semi-supervised learning, you can get a much higher accuracy, or you can maintain the same level of accuracy with much lower number of queries. And
the
then
number of queries they used was 140K, right? Is that the number of queries they use?
So the first one is only used 250 queries. And then
no, I'm talking about the table below. The
table below.
Yeah, for ImageNet they use 140K.
Yeah, 140,000 queries. So yeah, with that many queries, you get 83.5% accuracy. And then it got further improved with semi-supervised learning.
Got it. Thank you.
Yeah. For a smaller data set, it's much easier to get very high level of accuracy because there's only like, for example, CFAR10, they only have 10 categories. It's easier to categorize that. So after the accuracy, the author also want to talk about the fidelity. So on the prior work of Millie et al. And the Patinas et al.'s work, they proposed ways to extract the bias in a neural network. However, the Millie et al.'s work is only theoretical. It's never been actually show as code. So the author written that part and then make that work in Flow 64. So here's an intuition about how to do the model extraction. And in two-layer neural networks ReLU, we can visualize that by a 2D plane. So here it shows if both the ReLU function are 0 at the 0 region, so we only output the bias. And then at the top one, so only one ReLU function is working. And on the right-hand side is 2 ReLU functions are working. So we just pick a random point u and then get a vector v and then sweep this line until we meet a critical point x1. So x1 is the boundary between one ReLU function is working and the two ReLU function is working. By doing this, the sweep of line look like this. So at the beginning, all have bias, and then one of the linear region start to work. Until we reach x1, another linear region start to working again. At the critical point, we can extract the weight of a single ReLU function. And then we repeat this attack on all the perceptrons, all the ReLU part. We can extract all the weight in the first layer. So yeah, so here the intuition graph out all this. So we find the critical point where one of the ReLU function is either a 0 or just started to work. And then we subtract the left one with the right one. So the only thing left is the one ReLU function, and then we can extract the weight of that ReLU function. It's more complicated than that, but you can read the full paper to get the full details in the Millie et al.'s work. It's not really written detail in this paper. So after we're able to get one ReLU, we can get all the weight in the first layer. So as we can imagine, if we can get the weight, we can basically replicate the model. So here, the paper shows with like 12,000 parameters, we can get like 100% fidelity with 2 to the power of 17 queries. That's a lot of query, but we get the full fidelity. We get all the parameters, we get all the weight. So this shows this type of attack is doable. We can indeed get the full details about a 2-layer ReLU neural network. And then the author finds, so as the parameter gets more, the fidelity start to decrease. And then he wants to improve the fidelity even with more number of parameters. So before we mentioned, so we are kind of extracting the weight directly. However, we can combine that using gradient matching and error recovery. So using some AI to help us to guess that value. With that included, we can further improve the fidelity on larger number of parameters. Notice it's 4 times larger parameters, but we get similar fidelities. So our overall fidelity gets higher. But notice the query number is still very...
Sorry to interrupt you. I mean, we are over time. You can continue, and then I'm going to continue recording. But people, obviously, if they want to drop off, that's all right. But yeah, go on, please.
Yeah, sure. So this reviews some of the problems of this paper. So the inside interpretation are semi-supervised learning is effective when doing model extraction that is focused on accuracy. It can definitely improve the accuracy by only a few hundred queries, or for larger model, a reasonable number of queries. However, the functional equivalent model extraction on only like 2-layer neural network. It's a very simple network. Although it can reach almost perfect fidelity, but it requires a large number of queries. If this is like a paid service, 2 to the power of 20 queries on 10,000 parameters, that's just too much. So I think that's the reason why most papers are focusing more on the accuracy rather than the functional equivalent model extraction. And then
yeah, I mean, this is nice. I mean, there could be scenarios where number of queries is not a challenge. So for example, let's say you want to reverse engineer a local model. Let's say there is a mobile device that, design specific, model. And for some reason you have access to that mobile device. And now you want to reverse engineer to fully extract the model. So in that case, number of parameters is not important, but fidelity is, of course, is important.
Yeah.
But in more realistic machine learning as a service scenarios, as you mentioned, probably accuracy makes more sense because it requires significantly less amount of queries.
Yeah, that's definitely right. Yeah, so unless we have the local model, if it's like paid service, it's probably not doable. And then some potential future work. So right now, the paper only focuses on attack the neural networks with only 2 layers and with ReLU function. So maybe we can extend this attack to more than 2 layers, because any modern neural network will have more than 2 layers. Only toy network have 2 layers. And then further improve the number of queries needed to do the functional equivalent extraction. So 2 to the power 20, if we can reduce that by like 2 to the power of 10, then it's much more doable. And then explore this type of attack on other type of activation function. Right now, the author only focus on the ReLU activation. And we can extend that to like tangent, hypertangent function and other type of function. And then we can thinking about the defense techniques. In that paper, it only mentioned some defense technique, but we can definitely to use explore more on the defense side of this. By, for example, the author mentioned you provide less information can kind of cut down the accuracy of the model extraction, etc. So we can developing more defense techniques. And then, yeah, that's it.
Great, thank you. Yeah, I think I saw some work after this that's kind of like improved the functionality equivalent extraction a little bit. But yeah, I think there are some future works that's kind of like did this in order to improve it a little bit. But of course, it's still a big problem because essentially you're trying to solve a system of equations with many perceptrons and many different parameters. So basically your entire space is divided by this piecewise linear lines. So you need to find every single one of them. But maybe some sort of classification can help. There could be different ideas. Yeah. All right, thank you so much. Any questions, anybody? We are over time, but of course, if people wants to ask questions. All right, cool. So
Thank you very much.
Vishnu and Shreyas. Oh yeah, somebody had a question.
Oh, question. Oh, was okay.
No, you were saying something. Somebody was saying something.
Probably me. I'm not really asking.
Okay.
Sure.
All right. Yeah. So Shreyas and Vishnu, sorry about that. So we're gonna do it next week. Just FYI that Monday is holiday, I believe, right? Next Monday or not? Yeah, I think next Monday is MLK Day, so we won't have class. But I'll publish a video and we can have a meeting on Wednesday. All right. So thanks everybody, and see you soon.